Welcome to the second part of week 9 lecture for the fluid mechanics for chemical engineering. In the part 1, we have learned some basic examples on the Navier-Stokes equation, in which we have applied some assumptions and conditions to make a simplification of the Navier-Stokes equation. I want you to remember that we can make these kinds of simplification based on very important assumptions such as steady state assumptions to cancel out the time dependencies, and there's some incompressibility assumptions which makes the divergence of the velocity term is equal to 0. And in many cases, you need to remember that we can use some kind of a symmetry condition, which will reduce some dependencies on the specific directions. For example, in cylindrical direction, in cylindrical coordinate system, we can cancel out the dependencies on the axis symmetric dependencies. So it means that we can cancel out the derivatives of the velocity component with respect to the azimuthal angle direction, something like that. In the second part in this lecture, we will explore some specific Navier-Stokes equation cases, focusing on how we can deal with these differential equations to find out the velocity profiles in those specifications. Okay, let's get started. Now, let's look at some other specific cases considering basic assumptions and several conditions. The first case is the inclined path U flow. We have already learned this case before using some basic force balances, momentum balances, and mass balances. But for now, we want to solve this problem using the simplified Navier-Stokes equation. In this case, we will take RCCS for this problem too. We have the same conditions for the velocity components, such as Vy and Vz are equal to 0. In addition, we also consider no dependencies of Vx on x. This means that Vx is a function of y only again. Actually, this is due to our fact that we are assuming that the fluid is fully developed. It means that there will be no dependencies of the velocity component along x directions. Okay. However, in this situation, we have two body forces for x and y directions. The first one is what? Rho z sine theta, right? And the second one is rho z cosine theta. In addition, please note that we can only apply no slip condition at the bottom surface because there will be free surface on top of the fluid. So in this case, we only apply the no slip condition to the bottom. But there's another kind of boundary conditions such as moving boundaries or moving plates. In those cases, it is not possible to apply the no slip condition. Instead of the no slip condition, we will apply some constant velocity condition at the bottom or in the inner surface of the plate. Okay, so please focus on the problem description to find out the relevant boundary conditions to solve the simplified Navier-Stokes equations. Okay. From the simplified Stokes equation, we will obtain two differential equations on the x and y. The first one tells you the pressure profile here. The pressure profile such as profile as a function of y here, right? Using the boundary condition we mentioned in the previous slide, we can say that the pressure is what? Del negative y, right? Del negative y rho g cosine theta. Okay. In x direction, we can find that the double derivative of the Vx with respect to y here is equal to what? Rho z sine theta here, right? Divided by viscosity. For the boundary conditions, we can think about no shear stress condition for the top surfaces because the surface is exposed to the air, right? So it means that there will be nearly no frictional forces given by the air, and we can say that tau xy or tau yx is equal to eta rho del vx over del y here. And this will be equal to rho z sine theta y plus some constant C1. And using the boundary conditions at the free surfaces, which is at y is equal to delta, we can calculate or we can find the value of the C1 as negative rho z delta sine theta here. So using this constant, and we can find that this del Vx over del y as a function of rho z sine theta y negative rho z delta sine theta. So this means that we can find the entire velocity profile of the x direction as a function of the y, and there will be another known constant Cw, C sub 2 here, and using the boundary condition at the surface of the inner surface of the plate, which is at position y is equal to 0, you can calculate the value, remaining unknown constant C sub 2 as u here. So finally, we can find the final velocity profile as shown in this final equation here. Okay, this u means that the drag velocity of the lower or bottom plate. Okay. Actually, this is quite interesting problem when considering the volumetric flow rate Q. Using the previously found velocity profile in x direction as a function of y, we can derive the dependence of Q on U, delta, rho, g, and eta as shown in this first equation here. Interestingly, we can think about a specific case in which the net volumetric flow rate is equal to 0, which means that the upper movement here and the lower movement make no net movement of the fluid, which means that there is no net movement or transport of the fluid along x direction because these up and down movements will be cancelled out each other. Okay, so this condition indicates the situation where Q is equal to 0, and using this equation and using the velocity profile and volumetric flow rate, we can find some critical thickness of the viscous fluid as a function of U, eta, rho, z, and sine theta as shown in this final equation. It means that if you control the thickness of the viscous fluid, delta, as this square root, something like this, there will be no net flow movement inside of this viscous flow. And this is a very interesting case. It's based on Navier-Stokes equations. Okay. Now, let's look at another interesting problem which requires us to think in another coordinate system. In this problem, we want to know the velocity profile in the annular region, which looks like a donut here, right? So this white region here between the outer radius and the inner radius, and actually this is fixed in a cylinder, and this is the pipe, and the probe will move through these annular regions. So there is outer wall and inner wall for the fluid here, right? Okay. The flow is moving in z direction. However, this case is like cylinder, and therefore it's natural to select cylindrical coordinate system or CCS instead of RCCS. So for this problem, we're gonna select the CCS to solve Navier-Stokes equation. Okay. And for the simplification of the Navier-Stokes equation in CCS, we need to make some important conditions and assumptions. The first one is that the flow is sufficiently viscous and therefore can be considered as what? Laminar flow. And the second is that the flow is Newtonian and incompressible fluid. The third one is that all the physical properties are fixed. The first one is that the flow is fully developed, and I explained what this means in the previous part. Therefore, there will be no dependence of the velocity component in z direction on z. It means that there will be no differences for the different position along z directions. The fifth one is the existence of the axis symmetry. In here, the axis symmetry is z direction. It means that there will be no dependencies of the velocity profile on azimuthal angles because azimuthal angle has axis symmetries. Okay. The sixth one is the no-slip boundary condition at the inner surfaces of the plates. It means that there will be no velocity at the surface of the inner diameter and outer diameter. Okay. Finally, we will consider steady state for no time dependencies. In CCS system, these assumptions and conditions will allow us to say that the velocity components in radial direction and the azimuthal angular direction are equal to what? 0, right? So VR and V zeta will be 0 in our simplified Navier-Stokes equation. It means that there will be only z-dependent velocity component in this system. Okay, and there will be no time dependencies, and there will be no z dependencies for the z-directional velocity of the fluid. Using these assumptions and the conditions, we can proceed to make the simplification of the Navier-Stokes equation. Okay. For getting to the Navier-Stokes equation, it is always important to consider the continuity equation or mass balance in your system. First of all, let's think about the mass balance or the continuity equation in our CCS system. In a similar manner for the posi-U flow in RCCS, using axis symmetry condition, we can derive that the velocity profile in z direction is a function only on r, not on z, zeta, or time. So it is very simplified, the version of the velocity profile, because there is only one z-directional component here, and the component is only a function of a radial direction r here. So there will be no direction zeta, z, and time. This will make very simple version of the Navier-Stokes equation in CCS in next slide. Okay. Next, it is a moment to cancel out many terms, as many as possible, based on important assumptions, conditions introduced in previous slide to make the simplification of the Navier-Stokes equation in CCS. First of all, we will cancel out all the time-dependent terms here, right? Because we are dealing with the steady state conditions. And we will cancel out all the velocity components such as VR and V zeta here. Next, we will cancel out all the velocity gradient terms such as Vz over V del z is equal to 0, and Vz and over the del zeta is equal to 0 too. So in these equations, we will cancel out as many terms as possible, and for the gravity terms, there will be Zz is equal to 0, Gr is G cosine theta, and G zeta is negative G sine theta. Okay? And if you have some difficulties in understanding why the gravity in zeta and r direction are given like this, please refer to the schematic diagram or illustration shown in this slide. As shown in this slide, at some point inside of the annular region with the radius r shown in here, we can always define the gravity to the downward direction. So we can put negative sign here. So negative g is gravity at this position. And using some trigonometry knowledge, we can find the gravity forces for the zeta direction, r direction here, respectively. In particular, please note that there are two negative signs for the r direction, so negative g cosine theta. The first negative sign is due to this downward gravity at this position. And the second negative sign is the direction of the gravity. So it means that this direction from the center to the outward is the positive direction for the R direction. But the direction of this green arrow is inward. So it means that we need to put another negative sign for the R-dependent gravity sign here. In contrast, for the theta direction, which is at the circumference at this point, the gravity for the theta direction is equal to negative g multiplied by sine theta here. So for the gr is g cosine theta, negative, negative, positive, right? And g theta is equal to negative g sine theta. So further simplify the Navier-Stokes equation, we will use these gravity-dependent terms for the body forces. Okay, please check this relationship by yourself. Using the simplified version of the Navier-Stokes equation in CCS, we obtain three ordinary differential equations as shown on your left side here. And this allows us to find the pressure profile as the combination of the rho z r cosine theta and some function depending on z here. When you take first derivative for the pressure as with respect to z, and you will get this del f del z and this eta multiplied by 1 over r del r, and which is derivative for the r multiplied by del vz over del r here. And you can find that the red function here is function only depending on z, while this green function here is function only depending on r. So further make this kind of relationship, it means that the burst above will be constant, right? And let's call that constant as K1 here, right? And this means that we can obtain the FZ profile and the VZ profile using these conditions, okay? So far, so good. And first, let's look at the VZ as a function of R using the constant K1 here, right? So in the relationship introduced in the previous slide, we can say that this del F del Z is equal to K1 and del F del Z is equal to dP over dZ. So the unknown constant K1 is defined by the pressure gradient along Z direction. So we have found the value of the K1. And using these relationships, and we can integrate one and this first integration and the second integration, and you will find this kind of R-dependent function for the velocity profile in Z directions. And we have two more non-constant here. K1 is found dP dz here, but we don't know about the K2 and K3. And to find K2 and K3, we can use the boundary conditions, such as no-slip boundary conditions at the inner surface and the outer surface. Inner surface means that the R for the position at R is R1, we can say that the VZ is equal to 0. In a similar manner, there is no slip condition for the outer diameters, which means that the position R is equal to R sub 2. And using these two equations, we can find the value of the K2 and the K3 as a function of R1, R2, and pressure gradient here. And these final equations will be inserted to the final velocity profile as a function of R here, right? With this information, we can finally obtain the entire velocity profile of the fluid in annular region, such as these equations here. Please remember that we have a log function here in this equation. Actually, it is a typical function for the Navier-Stokes equation solution in CCS. So you will frequently meet this log function or similar log-like functions for the problems defined in CCS. Actually, using this velocity profile in z direction as a function of r, it is possible to calculate the volumetric flow rate Q, and the result is shown in this final equations here. Please derive this equation by yourself and for better and deeper understanding of the Navier-Stokes equation. Based on the volumetric flow rate, it is also possible to calculate the average velocity of the fluid inside of the annular regions between the inner cylinder and the outer cylinders. Okay, I will leave that for your practice. Please repeat this derivation and check yourself. Okay. Now, there is one remaining coordinate system to solve the simplified version of the Navier-Stokes equation. What is that? Yes, right. It is a spherical coordinate system. Actually, it is the most complicated coordinate systems, and therefore, it is always difficult to solve the Navier-Stokes equation in SCS. But please don't worry about that. We can make a simplification again for the Navier-Stokes equation in SCS too. However, it is true that even the simplified version of the Navier-Stokes equation in spherical coordinate system will require you to solve complicated differential equations such as second-order ordinary differential equations with some exponential or log or some trigonometric functions. Okay? Therefore, I strongly encourage you to review your engineering mathematics or differential equation courses for better and deeper understanding on the Navier-Stokes equation in spherical coordinate system. As one of the famous examples which use SCS, let's look at some experimental apparatus to measure the viscosity of unknown fluid, unknown Newtonian fluid. This device is called cone and plate rheometer or Weissenberg-Lagrange. This device accommodates unknown fluid between the cone here, right? This is cone-shaped plate, cone here, and plate, underlying plate regions, as shown in the cyan color region on your left figure here, and the cone and the plate here to rotate at some designated angular velocity at omega here, right? So by measuring the torque, which is given by the fluid between the cone and plate here, we can extract some valuable important information on the viscosity of the unknown fluid. So we will explore the detailed principles how we can measure viscosity from the measured value of the torque. Okay. For this, we need to solve some simplified version of the Navier-Stokes equation for these devices. Okay. As shown in this slide, the important variables in this case is the theta or some beta between the angle between the cone and the plate. We can define the angle like this one, or this one, okay? So please focus on your problem descriptions to find out what is the angle between the cone and plate, okay? And there is another important variable such as the radius of the cone or radius of the plate. And there's some kind of another variables such as angular velocity. So this will have some unit of RPM such as the rotation per minute, okay? So using these concepts and important variables, we can proceed to construct some governing differential equations. Similar manner to the CCS or RCCS for the previous slide and the previous part, we can make some important assumptions and conditions to make the Navier-Stokes equation in SCS as simple as possible. In particular, for this problem, we can make additional assumptions, such as there is no pressure variance in space. This means that no gradient of pressure in r, zeta, and phi direction in SCS. Based on these conditions and assumptions, we can say that the velocity components in radial and polar angle direction are 0, it means that the velocity component is a function only in azimuthal angle here, right? Pi direction here. And for the steady state condition, there will be no time dependencies for the velocity components. Okay. The first step, let's look at the mass balance or continuity equation in SCS. So considering axis symmetry, it means that there is no dependencies on this azimuthal angle pi here. There will be no dependencies on pi, and therefore the azimuthal angular directional velocity is a function of r and theta here, right? So it is very easy to understand why there will be dependencies on r and theta here, because the angular velocity is proportional to r, and there is some kind of confinement in the polar angle, which is defined by the cone and the plate here. So there will be dependencies on r and theta, but there is no dependencies for pi because there will be axis symmetry around the rotational axis. Okay. Before solving this ordinary differential equation, let's think about some situation. First of all, let's think about the situation of velocity profile component phi at r is equal to 0 position. What would it be? Right, there will be no movement, and the velocity should be 0 at the position at r is equal to 0. And considering the rotation, the velocity will be proportional to the distance from the position to the origin position. And therefore, the velocity in a phi direction will be proportional to r, right? Therefore, we can postulate that v phi can be written as omega multiplied by r multiplied by some specific function depending on theta here. So this omega is called the angular velocity, and it works as a proportional coefficient for this function for the v phi here. Okay, in this equation, we will say that there is the theta dependencies only for this f theta here. Okay, so it means that all you have to do is just find out the exact functional profile of f theta here, because we have already done the radial dependencies in this omega r here, right? Using this first relation and inserting this equation into the simplified version of the Navier-Stokes equation in SCS, we can obtain the second order ordinary differential equations as shown in this line here. And using some mathematical tricks, it is possible to derive some complicated trigonometric combination as shown in the final differential equation here. Please check this by yourself. Here is some procedure for those whom want to follow the derivation, how we can obtain this kind of the differential equations, which is combined with some sine theta and f theta here. Please check this by yourself. So using the differential equation derived in the previous slide, let's integrate, okay? Let's cancel out this, and there will be the sine cube multiplied by del theta, and the f of sine theta is equal to K1, and integrate again, and you will get this f of sine theta is equal to some constant multiplied by integral of 1 over sine cube theta. And it is important to know about how we can make this kind of integration, such as 1 over sine cube here. And actually there is some good formulas to understand this integration of the sine cube 1 and sine 1 over sine theta. And using these mathematical relationships, it is possible to calculate this integration function. And there will be two unknown constants which are required to define the functional profiles of the f as a function of theta here. Okay. Now it is time to find the unknown constant. Assuredly, for this, we can use boundary conditions. What are the boundary conditions? The first condition is at the bottom surface of the plate, or at the theta is equal to pi over 2 here, right? So this means that there will be boundary condition right on the surface of the lower flat plate. Okay, at this position, the velocity in y direction should be equal to what? R multiplied by the angular velocity omega here. Therefore, we can find out the value of the K2 as 1 using this equation. The other condition is no slip boundary condition at the cone surface. It means that at the position of the polar angle theta is equal to beta, the f beta is equal to 0. So using these equations, you can also find out the value of the another remaining unknown constant K1 here. So we have found K2 and K1, and therefore we can find the entire polar angle dependence functional profile of the f theta here, like this. Okay. This is a somewhat complicated form, but it is very fortunate to find out this analytic formula as a function of the theta, only theta here, right? In this case. And using the velocity profile found in the previous slide, it is possible to calculate the shear stress tau theta phi. Okay, so this shear stress means that the polar angle directional and the working direction is the azimuthal direction. So it means that there will be fractional dissipation given by the cone surface and the lower surface, and those shear stress can be defined in a theta and the phi direction. And based on the spherical coordinate systems for these tau theta pi, we can say that there will be no dependencies on the v theta here because v theta is 0, and the tau theta phi is defined like this. And using the finite velocity profile in the azimuthal angular direction, we can find out this form, and we can find out the f theta over sine theta. And using these results, you will get these finite relationships for the tau theta pi here. And please note that there is some kind of relationships for the viscosity here, and angular velocity here, and the cone angle beta here. All you have to do is just measure the angular velocity and beta to calculate eta here using the tau or shear stress here. But it is not always possible to measure the shear stress. So instead of the shear stress, we can measure another mechanical properties such as torque. So using torque, we can calculate the viscosity. Okay, how we can derive the torque from the shear stress? Actually, the shear stress at the surface of the cone it is possible to calculate the torque T, which is equal to the integrate value of the arm's length multiplied by the shear stress over the surface area of the cone. And the calculation will give you the final value of the torque T as a function of the angular velocity omega, radius r, and viscosity eta, and cone angle beta here too. So if you experimentally measured the value of the torque or mechanical torque using some sensors, you will find the value of the viscosity if the other values are known or measured. So this is the basic principle of the cone and plate rheometer of measuring the viscosity. Assuredly, there are many different devices of measuring viscosity. However, the cone and plate rheometer is one of the most frequently used devices for a wide range of the Newtonian fluid. Okay, thank you for your listening. This will conclude the second part of the week 9 lecture for the fluid mechanics for chemical engineering. And we will explore another interesting and some specific cases to work with Navier-Stokes equation or simplify the version of the Navier-Stokes equation. Please remember that you will need some important assumptions and conditions to make the simplifications. And based on that assumption and approximations or conditions, it is always required for you to check the relevance of the final solutions. Because sometimes the approximations or assumptions are not that physically make sense, so it means that the final solution will be meaningless. So it is always required for the student to check your solution by comparing with some physical manner or physical meaning. Okay, we will explore in detail about this in next lectures. Okay, we will see you later. Thank you for your listening.